Okay, good evening, everyone. Uh, in this live session, we will discuss the examples related to the week 12, and this is the last session for this course. So, if you have any doubt after this, you can ask from the discussion forum, or you can ask through the comment section of the where I upload the videos. So, let us start for this session in which we will discuss six questions in which uh, uh, maximum questions are related to the multiple choices. So okay, so the first question is the following is the basic requirement of the seismic isolator, like which one is the basic requirement for the seismic isolator. Okay, so in which like the options are given the high vertical stiffness with low horizontal stiffness, or high horizontal stiffness with the low vertical stiffness, or the high relative deformation in the superstructure with low deformation concentrated at the isolator level, and the lengthening of the period or the reduction in the displacement with the high energy dissipation. Okay, so what is the isolator meaning, why we provide the isolator? Like if you think about the isolator, what you hear, like when you think about the isolator, what comes in your mind? Like, is it the reducing the horizon, it is the reducing the response of the structure, or it is in the vertical direction or the horizontal direction? Like, suppose I have a structure which is fixed base, and another structure with a seismic isolator. Okay, so seismic isolator, what the seismic isolator do? Like for this structure, or vertical response for the ground motion, on the perspective of the ground motion, horizontal ground motion, what will happen? The structure will deform in the ground motion earthquake. Okay, so the there is a deflection in the columns. If we consider the beam as a rigid, so there is maybe some damage in the columns. Okay, but how we find out this, like this displacement is higher? Like for this spectra, if we go response spectra, in which such as this time period, like for the fixed base structure, time period is around some zero point 0.1 second or zero point 0.2 second, which is live in this range, between this range. So if we reduce for, if we will come in this range, then our displacement or the, this is the graph for the SA by G. So displacement or the acceleration will reduce. Okay, so if I shift my time structure time period to here, from here to here, what will happen? My spectral acceleration reduces. So in which, by using seismic isolator, I increase the time period. Okay, such as 1 second or 2 second, whatever the required or the effective time period. So in which the deformation will be taken place by the isolator. First, the isolator will deform like this way, and there is a deformation in the structure also, but not that much is a deformation in the structure. Like this is, if this is like 10 mm, then there will be deflection in the structure, maybe 2 mm or 3 mm, but not that much deflection, because the deflection taken care by the this isolator. Okay, so in the first option, so when this time period will be higher, like in which the time period of this structure is says t1, and this is the time period of t2. So for the isolated structure, the comparison of time period t1 is less than t2. This is for the isolator. Okay, and this is for the fixed base. So t1, so how my stiffness is depend? T1 is equal to 2 pi by m by k, and this is 2 pi by m by k. So my 2 pi will reduce, or if I will do it square, then that will become m by k 1. m by k2. If my time, mass is same in the both the structures, so my k2 will be less than k1. Okay, meaning the k2 means k2 for the isolator, when my time period for the my the stiffness of the isolator, and this stiffness for the horizontal. Okay, like for the vertical we are not considering in this, because for the isolator are normally for the horizontal, to reduce the horizontal response, not for the vertical. So in which the first option, like the high vertical and the like the low horizontal stiffness, first is thing, and the another is the vertical stiffness. So we don't want to deflect our structure, we don't want to deflect vertically our structure. So we provide, like as the, if there is a fixed support, so there is a infinite, we can say that there is an infinite stiffness, which will do not allow to structure deform, like do not allow to settle this vertical support. The same for the, if we provide the isolator, so for isolator we also provide the higher stiffness, so that it doesn't allow to the vertical settlement. So for this, option A is correct. And for the option B, because if the horizontal stiffness is very low, so one thing is that that is the disadvantage, because it will allow the vertical settlement, but also not effective for the, if we have a high horizontal stiffness, then there is not much difference in the fixed base and the isolated structure. So then we will not able to reduce the response. So that option is not applicable. Now come to the third option, like high relative deformation in the upper structure with low deformation concentration at the isolator. So with the isolator, what happen? With the isolator, what happen? If we apply a isolator to a structure, so horizontal deformation taken care by the isolator first. Isolator take the horizontal deformation, okay, and then, like says, if over, like in the fixed base we are getting the 10 displacement, so the only like around 8 or the 50 or 60% isolation or 80% isolation is achieved says. So the 80% displacement is taken by the isolator, so only 2% displacement, 20% displacement is taken care by the structure. So the high relative deformation in the superstructure, so there is a no high, so this option is the wrong, because the relative deformation in the isolator is higher than the superstructure. Okay, and same for the low deformation concentrated in the isolator, no, because the high deformation in the isolator and the low deformation in the superstructure. So this option is also incorrect. Now for the lengthening of the time period, reduction in the displacement with the high energy discipline, yes, that option is correct, because isolator we are using like our may like to reduce the stiffness, of the isolator. Okay, fixed base or time period of the isolator would be higher compared to fixed base. So for the time period is higher, mean in the spectra, if we increase time period, like for the, to reduce the stiffness we need to increase the time period of the structure. So first part is okay, length of time period. Another, the reduction in the displacement. But when the, like the, in some cases, like if we increase the time period, like time period is increasing, means our omega is decreasing. Okay, so displacement is, what is our displacement? Acceleration divided by the omega square. So as the omega is decreases, our displacement is increases. That is the one question. So for this, if we apply the damping to the system, high damping, so that if we apply the high damping, our displacement will definitely reduce. So reduction in the displacement with the high energy dissipation. So we if we provide the damping, so our this curve is shifted toward the lower and lower and lower. So that's why we over energy, with the help of the high energy dissipation and the lengthening of the time period, we can achieve the isolation of the structure. So our option A and option D are correct. Okay, so I have written the statement also, like you can go through this statement. Like the basic requirement of the base isolator is to have high vertical stiffness with the low horizontal stiffness, as I discussed, to reduce the acceleration response in the horizontal direction by lengthening the time period. At the same time, the displacement response has reduced using some external energy dissipation, because it will become high as the time period is increases, means our natural frequency is decreases. So that's why displacement is increases, so that we are using the high damping devices such that our displacement will reduces. So option A and option D are correct. Okay. Now let us go to the another question, in which what is the desirable fundamental mode of vibration for the base isolated structure? Like you have given a deflected shape of a building with a isolated. These are the isolated. Okay, isolators. These two are the isolator. Okay. So in the first building, there is no deformation in the isolator, only deformation in the superstructure. Okay. Let us say US. In the second case, there is a deformation in the isolator US as well as UB in the isolator. In the third case, there is a deflection in the vertical deflection, like there is a VB downward. In the last case, there is a deflection in the isolator UB, and there is a negligible displacement. There is a displacement, but that is US is order to zero order, like not much higher. So, which is the fundamental mode? Means the predominant mode, first mode of the structure. So, for the isolated structure, like if we go to this option, if there is a no deformation in the isolator, UB is 0 and US deformation, that means this is not a isolated structure, not isolated effective, because there is a first deflection in the isolator, then some remaining deflection in the superstructure. So this option is discarded. Now in the second one, there is a deflection in the isolator UB, but there is significant deflection in the superstructure also. So that option is also discarded, because there is a predominant deflection in the isolator. Isolator. In the third option, there is a vertical deflection, means the stiffness of the isolator, vertical deflection of the isolator is low. So for the isolator case, our vertical stiffness is very high. Okay, compared to horizontal. Like horizontal stiffness is very less as compared to superstructure. So this is not a actually a isolated mode. Now come to this, in which we have deflection in the first isolator, and there is a not much deflection in the superstructure, around order 0. So this is satisfying our definition of the isolator. Okay, so option D is correct. Okay, so the mode shape should be such that mode shape should be such that it should have high lateral deformation at the isolator level with very low deformation in the structure. Okay, like in the isolator, the deflection of the UV should be higher than the superstructure. Okay, so this is was our question 2. Now, hence the option D is correct. Okay, now come to the another question, in which we have given a the frequency of the vibration for base isolated structure and the fixed structure, considering, like, first go through the question one by one. Like the frequency of the base isolated structure and the frequency of the fixed structure of of a structure considering STF system is given by omega b and omega s. Like saying that that is my first structure which is fixed base, and my structure with base isolated. Okay, so for this omega, like this is a stiffness of Ks, stiffness of the column, and the mass m. So omega s would be the Ks by the m. For the base isolated structure, let us say this is the mass of superstructure and this is the mass of the base. Okay, so the, and this is the Ks and the stiffness of the isolator is the Kb. So in which the Kb is much lesser compared to Ks. So deformation in the, like we are ignoring the deformation in the superstructure. Okay, no deformation in the superstructure. So our omega b would be the Kb divided by total weight m plus mb. Okay, so these two frequencies are given to us. If what are the modal frequencies of the base isolated, these are the frequencies when we consider the our isolated structure as a equal and single degree of freedom system, says the SDO. If what is the modal frequency of the base isolated structure considering it has 2 degree of freedom system, like if I have a base isolated structure, mass m, mb, ks, kb. So I considering this as a 1 degree of freedom, this consider as a 2 degree of freedom, 1 and 2. Okay, so what will be this omega 1 and omega 2? Okay, so what are the modal frequencies of the base isolated structure? Like omega 1 means what is the deflection of the frequency of omega b in this case of the when we consider it as a 2 degree of freedom system. And there is a parameter is given us that the ratio of omega b by omega s, frequency of base isolated and the frequency of the superstructure square is around 10 raised to power minus 2. Okay, means the frequency of this omega b is very lesser. Omega b is less than the omega s, so the ratio would be in the order of 10 raised to power minus 2. Okay, so this thing, and there are other thing also has given that the m is the total mass of the base isolated structure. So m is the, what is the m? M is equal to m of the mass of superstructure and small m b of base mass of base mat. Okay, and the kb and ks are the stiffness of the base isolated system and the ks is the stiffness of the superstructure. Okay, so these things are shown in the figure. I have also draw a figure so that will clear your doubt. So this is my isolated structure. In this is the mass. This is the mass of superstructure. This is a mass of base mat. This is the stiffness of the superstructure. This is the stiffness Kb of the isolator. So if the structure is deflect, if my structure is deflect, so like let us say there is a ground motion, Ug, ground motion, Ug double dot or Ug. So due to ground motion, first there is a rigid movement of the structure, which is Ug. In which in that time there is no deformation in the structure and the isolator. Then deformation in the isolator, which is Vb, like isolator is deflecting by amount of Vb. Okay, and then there is a deflection in the structure after, like remaining 20% deflections is which is ds in the superstructure. Okay, so this is our 2 degree of freedom system. So we will take the write the equation of the two degree of freedom system by one. Like first cutting the structure from here, then cutting the structure from here. Okay. So let us write the equation. So for this, first let us cut the system at the bottom from the isolator, in which like this is the diagram I have shown you in the previous slide. Same diagram, only that I have cut the structure in the above. So in which if I have cut this structure from here, so above this, what are the deformation? Like what are the force? So this M, there is a force in this which will be the mass times the acceleration, and the acceleration will be the UG double dot VB double dot plus Vs double dot, because that mass is gone from this, like first UG and then VB and then Vs. Okay, and for this mass MB, the acceleration would be the UG double dot plus VB double dot, because the Vs in the upper part. So the force, acceleration force would be the mass UG double dot VB double dot Vs double dot plus MB UG double dot VB double dot. Okay, and then now we are cutting our structure from here. So the stiffness force of the isolator will only take. Note this, like whatever the internal deflection which will not taken care by the this isolator stiffness. So that will be the force by the isolator, which will be the KB time the VB, like whatever the relative displacement, not the total, because the ground motion is the UG, that is the rigid displacement. So that will be the not in this our structure will not deform. So that will be the KB time VB is equal to 0. Okay, so I have write this mass UG double dot Vs double dot Vb double dot plus mass base weight UG double dot Vb double dot plus Kb time Vb. Okay, this I have written. If you solve it further, like taking the UG term in the opposite side, says that will term will remain with the M plus MB into VB double dot plus M into Vs double dot plus KB into VB is equal to minus M plus MB time UG double dot. Okay, so I have written this same equation. Like these two terms will go in the opposite side with the negative sign, and these are combined with the Vs. Once a VB is with this M and the VB with this MB. So I have taken the VB as a common, so that is the correct equation. Okay, now we are taking the we are cutting our structure on the other part from here, like considering the superstructure I'm cutting here. If I cut the superstructure here, in which my mass is only deflected by the mass time UG double dot plus Vs double dot. Okay, also VB double dot, because there is the overall deformation, no? VB double dot. Okay, and there is a force, stiffness force, that would be Ks time Vs. Okay, so if I write my equation, that will be the M time UG double dot Vs double dot VB double dot plus Ks time Vs is equal to 0. So that will become my equation as a M VB double dot M Vs double dot plus Ks Vs is equal to minus का M UG double dot. Okay, so same equation I have write here, same how I write it. this m ug double dot plus vs double dot plus vb double dot plus ks vs is equal to 0, and then I will send it, like I have sent it m ug double dot in the opposite direction. So my equation will become as a this mvb mvs ksvs minus mug double dot. Now if I combine equation 1 and equation 2 in the matrix form, so after combining these equation I can write equation by this. Like this is my equation 1 first row, and the second is the second equation. So this is m plus mb, m this term, if we multiply m vb dot vs, this is this term, and kb vb and ksvs this term, and that is the opposite term. Here we can consider also the stiffness damping term also, but here we are not using that, like in this, because we are only focused on the model frequencies. So here there is not use of that method. Okay, else you can add this matrix also, that will same as it, like plus, that would be the cb cs time vb dot and vs dot, same, not much different. Okay, so don't think about that in this case. Now we need to solve the eigenvalue problem. Like one thing is there, like our total mass of the structure m is mass of superstructure and mass of base matter. So that will replace with the capital M. Okay, so I have written this. And one thing is that we have taken a factor which will be used in the upcoming solution, a gamma, which will be the mass of the superstructure divided by total mass. Okay, that will be used further. So that is the a ratio, that is the mass of superstructure m divided by the capital mass, which is the total mass. So now we are going to calculate the eigenvalue and as well as the eigenvector. Okay, so let us go one by one. So the eigenvalue problem for this k minus lambda m is equal to 0. So k is given as over kb 0 0 ks time lambda, and lambda is given as capital M, small m, small m, small m. Okay, so we will write it as a kb minus lambda capital M. Remember this one, lambda and all the small m na, only there is a in the m11 there is a capital M, ks minus lambda small m, and we need to take the determinant of this. So I have write this equation from this. Okay, now take the write the equation, multiply this and this. If you write this, this become this, and this is the second term will become this. And if you will further solve it, like there is not much thing, like first kb will multiply this term, and then lambda multiply with this term, and this is the same. Now we are doing some mathematical manipulation, in which, like, initially we can take the some things outside lambda square and lambda, so that if I take lambda square outside with the lambda mm, so that will remain 1, and that will become as a m by capital M, like m square divided by m small m and capital M. Okay, so that will cancel out with this, so that will become as a small m by capital M. Okay, so that term in which that lambda is taken out as outside, so that will become an mkb and capital mks, and that is the same. So remember in the last slide I have shown you that gamma is the small m divided by the capital M. So I will replace this as a gamma. Okay, so that thing I will do, like the we can replace it with the gamma. And one thing, I divide this equation with the whole on the both the side by capital M times small m. So if I divide this equation with this, what I will get, like this equation divided with this capital M small m, and this divided by the capital M small m. So now in this equation I can write it as a gamma. Okay. Now let further modify rearrange this. So in this is the same, and in which the m kb divided by small m capital M. So small m will be cancelled out, so that will become as kb by m. Okay. And for this second term capital M, ks divided by capital M small m, so that will be cancelled out, so that will remain there. And in which I can rearrange this kb divided by capital M, ks divided by ks. Now I need to write the equation like this. I will replace with the gamma. Okay. And this I can replace with the omega b, because we have discussed, like, for the single SDF system, that omega s is the ks by the small m, k by m. And for the base isolated structure, in which this is m, this is mb, that omega b would be the kb by m plus mb. And what is this? This is our total capital M, omega b divided by kb by capital M. So that replaced with the omega b square, and that replaced with the omega s square. Okay, same thing with this. This is omega b square, and this is omega s square. Okay, so if I will replace these terms, I get my equation. Okay, I get my equation. Yes. Now this is the 2-degree polynomial equation. So now I need to find out the roots of this equation. For the polynomial equation, how can I find out my roots? For this polynomial equation, if I have an equation like ax square plus bx plus c, then my roots are x is equal to b plus minus under root b square minus 4ac divided by 2a. Okay, this way I can find out my roots. So in which, in this equation, what is my a is the 1 minus gamma. What is my b? Is minus omega b square plus omega s square. Okay, and what is my c? Which is omega b square and the omega s square. Okay, now I will put these things into this equation. Okay, so for this I have write the equation in which b, as b is the, sorry, that is coming out to minus. Okay, so that minus b become as a plus b, so this become as a omega b square plus omega square plus minus b square omega b plus omega s square minus 4. A is the 1 minus gamma, and c is the, that there is some typing mistakes, like I have written the further steps here. So that will be the omega b square and omega s square. Okay, so uh, like further I will take the omega s outside from this equation. Okay, so if I will take omega s outside from this equation, and that's 2 1 minus gamma is also take outside, so that is the 1 minus 2 minus 2 into 1 minus gamma is outside, and the omega s square if I will take outside, that will become as a 1. This term become as a 1. This term become as a omega b by omega s whole square plus minus in the root square. If I will take omega s power 4, if I will take, because that will become as a omega square outside. So in which that is become as the same, and in which, like, if I will take omega s 4 outside, so that 1 power is cutting by 2, cutting after this, we will get omega b square by omega s square, which I have written here. Okay, minus 4 1 minus gamma. And we have discussed like over epsilon is the omega b over m omega s square. Okay, so we will replace this with the epsilon. Okay, so if I will replace this with the epsilon, what my equation become, it become as a this one, like this was the omega b by omega s square. Okay, this was also omega b by omega s square, and this was also omega b by omega s square. Okay, so after writing this, now to solve this equation, or further we can like further we will first solve this root. So for this 1 plus epsilon square whole square minus 4 1 minus gamma epsilon, if I will do the whole open this square, so that will become a 1 plus 2 xi epsilon square, and that will become minus 4 epsilon plus 4 gamma epsilon. So if I will rearrange the again equation, that will 1, and that will become as a minus 2 xi, and that's epsilon, and 4 gamma xi. So epsilon is, as we have discussed, epsilon is in the order of 10 raised to power minus 2. So now if we do the epsilon square, so that will become epsilon 10 raised to power minus 4. So as compared to other things, 1 and this 1, that will be around 0. We are doing the approximation. So remaining equation will become, remaining equation is that 1, and minus 2 xi we have taken outside, so that will become 1 plus 1 minus 2 gamma point 0.5. Okay, so now we can write our equation, and this we know as 1 plus nx 1 plus x power n is expanded as 1 plus nx so on. Okay, so in this equation, what is my x? X is minus 2 xi 1 minus 2 gamma, and n is 1 by 2. So in this, if I will replace it, so that will become a 1 plus 1 by 2 into 2, like minus 2 xi 1 minus 2 gamma, so that will cancel out, so that will remain as a 1 minus xi, sorry, epsilon 1 minus 2 gamma. Okay, so this is remaining. Okay, so now I will replace this is this term here. Okay, so after replacing that, my terms become, equation become as a lambda is equal to omega s square 2 1 minus gamma 1 plus epsilon plus minus 1 minus epsilon 1 minus 2 gamma. Now I will take one by one. Once I will take plus signal plus sign, once I will take negative sign. So let us initially, I am taking the negative sign. So when I will take the negative sign, when I take the negative sign, this one, and if I will open this again, multiply with this minus 1, so that will cancel out to each other, and I will remain with this equation 2 epsilon 1 minus gamma, and that will cancel out each other. Okay, this one, this one, this one. So only finally I am left with the omega s square time epsilon, and as epsilon I know omega b square by the omega s square, so that will cancel out, so that will remain as the omega s square. So my lambda 1 is become as a omega b, sorry, this omega b square. Okay, so that will left as a omega b square. Now in the next part we are considering this plus part, this part plus side, in which if I consider it as a plus and then open this whole equation, so in which the epsilon will cancel out each other, and that will become as a 2 into 1 minus epsilon z. So this epsilon gamma, actually gamma is approximately we can say around 1 or zero point 0.8 something, and the epsilon is a 10 raised to power minus 2, and that is compared to this one which very like very negligible quantity. So here we are also considering this epsilon y is a 0. So if I will consider epsilon y as a 0, So my equation finally become as a omega s square divided by 1 minus gamma. Okay. So my lambda 2 lambda sorry my lambda 2 become as a omega s square 1 minus gamma. So I can write my omega 1, like what is my omega 1 is the square root of lambda 1, and omega 2 which what is square root of lambda 2. Okay. So my omega 1 is the square root of lambda 1, that is coming out to be omega b from this equation. And for the omega 2, that is a square root of lambda 2, and that is coming out from this equation omega s divided by 1 minus gamma. And if I will write the value of the gamma, that is gamma is small m mass of superstructure divided by capital M. Okay. So if I write this as, and if I will rearrange this terms, so I will get I omega s is equal to square root of capital M divided by capital M minus M. So these are my model frequencies, omega 1 and omega 2. Okay. So my first like the omega b, what was the omega b? What is the square root of kb by capital M. And for the omega to become as a omega s times this factor, and omega s was the ks by small m multiplied with this also. Okay. So these are our two model frequencies. Okay. So this was our question in which that we ask for the model frequencies. Now come to the another objective type questions in which if the damping ratio is increased, what will happen? Increase the displacement response of the system, increase the acceleration response of the system, increase the displacement response of the system, because if we increase the damping, the displacement response will not increase, that is wrong. Increase the acceleration response, also increasing the damping will not increase the response. Reduce the displacement velocity and acceleration, yes. Damping ratio has no impact on the response resistance, no. Damping ratio has a significant impact on the response quantities. Okay. So our option C is correct. Okay. So then increase in damping ratio with reduce increase in damping ratio with reduce with increasing in the damping ratio is reduce the displacement velocity and the acceleration response of the system. Now coming to question 5, in which we have what is the incorrect statement about the base isolated structure. Okay, incorrect statement. First statement is the it works on the principle of the lengthening of the period and enhancing the damping in the superstructure. Yes, it is correct. We have uh, studied in the like in the first question we have gone that it works on the lengthening of the period and the increasing the damping of the structure. Second is the effectiveness of the isolation system depend on the frequency ratio of the superstructure of the isolator. Yes, that there is a significant difference between the isolator frequency and the isolated frequency and the superstructure. So that will also affect. It reduces the drift in the superstructure but increase the displacement in the isolator. Yes, like as if this is the isolator structure, so that deflected shape would be the first isolator would deflect, and then our structure will deflect slightly. Like after deflection of the isolator, our structure is this, and there is a significantly, not much significantly, small deflection. Okay, if there is a no isolator, then our structure will deflect like this. That much. Okay, so it reduces the drift of the superstructure also. That is correct. It work on the principle of increasing the structure capacity instead of the reducing the seismic dam. No, with the isolator, we increase the time period of the structure, and with increasing the time period, our seismic demand will reduces. Okay, so it works on the reducing the seismic demand. Not it doesn't increase the capacity of the structure, but reduce the seismic demand. So this is wrong. Like it it doesn't depend on the capacity. So or option D is correct. Now coming to the last question of this chapter, this live session, and the whole chapter, whole course, the NPTEL, in which we have given the time period of the structure of a fixed space structure is given as a zero point 0.6 second, and the mass of the superstructure is given as a 100 ton. So it is proposed to be seismically isolated using a base isolator. So what is the following stiffness of the isolated system would be effective in the isolation of the structure? Like if we have given the stiffness of the like the time period of the structure, and it is given as a mass of the superstructure. So what would be the stiffness of the base isolated KB, not the case, like in which if so, like, like this is the mass, this is the mass of base part, this is your isolator. Okay, so the mass, like total mass of the superstructure, let us this combined mass we can consider it is our mass m is equal to given as a 100 ton, or multiply it with the 1000, that will give the 10 raised to power 5 kilogram. Okay, and the time period of the structure is given as a zero point 0.6. So what would be the stiffness of the KB isolator, not the KS? Okay, so for this we will first calculate the stiffness of the superstructure. So that can be calculated as a time period is given as a zero point 0.6 second, mass is given as a 10 raised to power 5 kilogram. So the stiffness of the superstructure can be calculated as a omega is given as a Ks by small m. So that will become omega square. Sorry, that will be the Ks by m. So Ks would be the m omega square, and that will be the 2 pi square by Tl. Okay, so that is the stiffness of the superstructure. And if we solve this, we are getting our stiffness is around 11,000 kilonewton per meter. So compared to this, and look at these four options, which stiffness is most suitable? Anyway, all these stiffness are suitable because as if we compare, as we have discussed in the first question, like the stiffness of the isolator KB is less than, much less than the stiffness of the superstructure. So this stiffness is also applicable, this stiffness is also applicable, this is also applicable, this is applicable. But most suitable, most effective, when it will be when the stiffness of the isolator is much lesser. So in which option A is given as this. Like the if we use the stiffness of the KB as a 1000 kilonewton per meter compared to this 11,000 around. So our isolator is most effective. Okay, this will also effective, but as the stiffness is reduces, isolation will give the most effective results. Okay, so in this option, option A is correct. Same kind of problem will happen if I have given you something. A question is given to you, like if I have a mass and stiffness of the superstructure, says mass is around 250 ton, stiffness is around 1000 kilonewton per meter, and if we this is the property of the superstructure, and then we calculate the, let us say, time period is coming around 1 second. So this is the mass of the superstructure base isolated. Sorry, I'm giving you the things for the, these are given for the base isolated. and the time period is coming out to be 1 second. So if I'm giving the option t is equal to zero point 0.5 second, zero point 0.6 second, zero point 0.7, zero point 0.8 second. So what is the most effective time period at which my isolation would be the effective? So in this case, you have given the isolator properties. Like the isolator time period is given as a 1 second. So the what is the time period of the structure should be that over your isolation would be effective. Like as it is okay that superstructure is zero point 0.8 is it is also less than the 1 second. Like time period of the superstructure should be less than the time period of the base isolated structure. So if we go with this time period zero point 0.5, we definitely achieve the most effective isolation. So for this, you have to first look up the like the options. What are these? Are the some like the judgment basis questions, not the if you calculate this time period and then thinking about how we relate the time period of the superstructure with the base isolated structure. You will never find out the answer. Some questions. So these kind of questions you have to with the you have to judge like judgment your judgment should be like that, like look at the options, like what would be the most effective, so that will be the point 5. Same kind of question with the if I have given you the like in this the mass of the stiffness is the given mass and the time period of the given structure is given. Let us say I'm giving you the stiffness is 4000 and time period is the zero point 0.6 second, and the mass you need to find out the mass, and the options of the mass are the 250 kg ton, 200 ton, 150 ton, and the 100 ton. So you need to find out the period of the like the like the at which what is the mass of the base isolated structure at which your isolation would be effective. So for this you need to also consider like as my mass is increases higher, my time period is higher. Okay, so T is equal to 2 pi m by k. So if I increase the mass, if I use this mass, my time period would be the higher of the base isolated compared to this zero point 0.6. So that will give me the effective most isolation. Okay, so these kind of questions you can solve with the judgment. Okay, so these are the questions which I have discussed in this session, and if you have any doubt related to this or any previous sessions, you can ask from the discussion form, or you can ask it from like the comment section from the YouTube channel where I uploaded it. So I am here like up to 7. If you have any doubt, you can ask, and thank you.